And the floor is yours, Alex.
Thank you so much. Sharing screen. I am on just one screen right now because I'm traveling, so I hope it works. So very loud noise.
Yes, it works very well. Please continue.
Sorry, there's an ambulance directly in front of the door. Let me wait a moment. Okay, now it's a bit better. Hope it's not too loud. Okay, so yeah, thank you for the opportunity. So this is about AVQ bits. Maybe some of you already know this. It's a generalization of the P1204.3 model that is part of Peanuts phase 2. I'm presenting on behalf of Rakesh Rao, Ramachandra Rao, who you probably, most of you know. He's already in his well-deserved vacation, and so I'm taking over for him. Yeah, and it's a collaboration also with Steve Goering, of course. Yeah, and so it's a bitstream-based model, and I showed the details now. So I hope this is readable. It's a bit small. So this is the general architecture. So the general model, which is this, we call it AVQ bits for bitstream M3, right? So these slashes here, they're always signifying what kind of mode we're in. That's mode 3. So that's the principal model, and that's identical to this ITU-T recommendation P1204.3, which we have already reported on a few times. So what it does is basically have a decoded video. Yeah, no, sorry, I have a bitstream parser. This is the hybrid model. Sorry about this. So this is the main branch. So you have a video segment and you have a bitstream parser. You aggregate the features. You do this for the coding impact, the possible upscaling impact, frame rate impact. And then based on this, you have a first instance of the model, right? And then in addition, you have a random forest predictor, which basically uses information about motion and a bit more detailed information about, yeah, let's say quantization impacts at frame level, and feeds this in and basically predicts a difference in training. There's a difference being trained here for this P1204.3 model, and then this is basically added in order to correct the generalized model output, which, for example, in case of this P1204.3 model is QP based. And then you get a prediction, and the weighting is, so it's first of all anyways already also using the direct MOS output here from this module in this prediction. So, and in addition, it is a relatively conservative weighting. So the random forest part is relatively mild in its contribution. So it's really just correcting for things which, for example, are due to content complexity, motion, whatsoever, that are not properly captured purely by QP here. Okay, so that's the main branch, which is basically this main model. And now we have developed a few spin-off models of this. Mode 1 model, I will explain in a few minutes what that is, or a few seconds, probably more. Then a mode 0 model, that's the classic, which you may know, is basically just parameter based. So you could apply it at the RPA level of, for example, some YouTube or the like. So you just use bitrate, frame rate, resolution, and which codec is being used. And then there's a hybrid model for which we are proposing a new idea. This is all based on I mean, this entire thing has been published in IEEE Access earlier in the year 2023, and also the code is publicly available under these resources here. Okay, and what I will be showing is basically this, this hybrid mode where actually a decoded video is re-encoded. Basically knowing in terms of a mode 0 model, knowing which codec is being used, then ideally you could actually re-encode it with the exact same codec that has been used, maybe even with similar settings that this mode 0 model would be detecting in terms of bitrate. Or you could also use a cross, so an inter model, so to speak, an inter codec model. Inter here and intra does not mean like intra and intercoding, but it's actually a little bit of a word game, quotation marks. So it means I'm using the same codec or I'm using another codec basically for this re-encoding, and then you apply this bitstream model out of the box, this P1204.3 model. and get your prediction. Yeah, and what I will show you in this presentation is quickly run through the four modules and then application scenarios beyond classical 4K video, 2D video. Okay, so the model description, I think I went through this already, so maybe it was a bit small, but just so this basically provides this part here, the coding part is codec specific, the upscaling and frame rate parts, they are general, and this codec specific part has some individual weightings for what is the QP range, etc., and is in the beginning basically just a QP based model, and then, as I said, it is corrected with this random forest model, and then you get a prediction. And you can see here that the final prediction is really this parametric QP based 0.5 times plus 0.5 times this random forest. And as the random forest also takes in this parametric model here, the contribution of the random forest part is relatively mild, which is actually, of course, limiting the success of the random forest part, but it increases the ability to be also working well for something unknown, right? So there's very little probability of complete overfitting. And the core model, this one here, so it's based on QP, display encoding resolution, display encoding frame rate. Yeah, and this random forest part here, so the machine learned part, as indicated, so QP, average motion per frame, horizontal motion, frame size and frame type, bitrate, resolution, frame rate, and the core model output here. Okay, and this is identical to the P12043 standard. So the mode 1 version, you see this part here, this machine learning part is omitted here, right? So there we have a feature aggregation which tries to predict exactly the same input to this model. So it's basically working using a QP prediction, okay? So you have as input metadata, so resolution, bitrate, frame rate, video codec, so something that you could even possibly get from some API. Then frame type and frame sizes, so some player info, and then at the core it uses this mode 3, the original standardized model in an unchanged manner, and the affected component is really just this quantization codec degradation component, which is the only mode dependent one. And here we are doing a QP estimation, right? So we are actually not adding these individual values directly, but and frame type and frame size, but rather we have a QP estimator and feed then the QP in this base model. Mode 0 works in a quite similar way. Now the input is even more reduced, so it's only resolution, bitrate, frame rate, video codec. And then, I mean, which video codec basically, and then it uses again the mode 3 P12043 core model, and again it's a QP estimation that is used as at the input, and that is now purely done on metadata. And you can imagine that from mode 3 over mode 1 to over mode 1 to mode 0, that you have a loss of precision. For those who are not familiar with this nomenclature of the modes, this really comes from our work in question 14, which of course involves also quite a few other parties. And there in this peanuts phase 1, we had also a mode 2, but this mode 2 has been omitted, but just for consistency, we're still using mode 3, mode 1, and mode 0. So that may sound a bit surprising. So mode 2 has been omitted for historical or technical reasons. Okay, the hybrid mode is something to shortly look at again. I mentioned how it works in principle. So you have the decoded video, and then you have two options of re-encoding it based on the metadata. You could be selecting the same encoder in pretty similar settings for re-encoding, or you could be basically using another codec at a specific setting, right? And then you feed this in, and then, I mean, of course, it must be a codec that you're using for re-encoding that the respective model knows. So the bitstream parser must know it, because then we are applying our bitstream parsing and then the analysis based on bitstream information. And in case of the training, this is obviously trained with this training data set. And this could also be for this QP estimation that we there have a little bit of a larger training set, of course. Yeah, and the central idea is in the first step, you recreate a quality equivalent bit stream. And that's, of course, best doable if you have the metadata and then you are trying to use exactly the same setting as have been used by the initial one. And there's state of the art that shows that if you are transcoding video with exactly the same content once more, with the exactly same video codec setting once more, that you have a very little change in video quality, right? And so we can assume that the bit stream looks relatively similar, right? If you apply it like this. And we will see from the results that actually works astonishingly well. And so the second step then is you do a quality prediction, and here it's a slightly modified AVQ bits mod 3 model, but it's only modified in specific weightings here, and it's a fixed modification which comes with this hybrid model. The good thing is you only need the decoded video plus this metadata. Obviously, it doesn't necessarily scale perfectly in terms of performance, because you have to have this kind of re-encoding, and depending on how powerful the initial encoding was and how much you know actually about the initial encoding, this may either take time or be leading to a bit stream which is not exactly identical in terms of quality. But for the tests that we carried out, you will see it's actually quite good. And then there are these two instances. So one is this HO/S here, and the other is F. And in case of S, it's the same codec as the original bitstream. And here, in case of F, we have been using H.265, so one predefined codec. Could be another one, of course, and then you would be training it slightly differently. Okay, I hope it's clear how these model variants work. And yeah, now how do we do the model evaluation? So the data set is our open source data set, AVT, VQDB, UHD1. And the metrics are person correlation and root mean squared error. This is the root mean squared error has been the criterion that has been used also in the Peanuts phase 2 competition, also in phase 1 competition. And then the AVQ BIS comparison, the mode 3 is the best performing. The HOS is the hybrid one based on the mode 0 version. It actually works almost on par to this M3, although it only has this initial information plus the decoded pixels as input. So it is not like really a no reference model, because it has this additional information about frame rate, resolution, bitrate, and which codec has been used, but it is really very little additional information that it uses beyond the decoded pixel information. And then the F, same information, of course, but it has a more sophisticated codec mapping, and then you also get an increased prediction accuracy even with another codec being used. And then this mode 1 and mode 0 variants, they're obviously the least well performing, because it's pretty clear the least real information about, for example, which content has been encoded is available. Then in comparison with state-of-the-art models, VMAF is the best performing pixel model. Obviously, actually the mode 3 and also the H0 are both outperforming VMAF. So here, to be clear, we're using the 4K version of VMAF in the latest version that was available at the time. And then mode 1 and mode 0, they outperform the best performing no reference pixel models, so BRISC and EEG, and of course are slightly or significantly worse performing than the H0 and M3 versions. And to remind, this Peanuts phase 2 running in ITU study group 12, Q14, leading to this AVQ BITS M3, is the P120.4.3 is in this comparison the best performing one. Okay, and this is shown here. So it's all in this Access paper if you want to know the details, right? The real numbers. But here you can see it relatively well already from the correlation, right? So this is the predicted MOS and this is the MOS. So to be very clear, this model has not been trained on this database. So it's an unknown database just for validation. And you see the loss in performance between M3 and M1. And then it actually is quite tidy here on the bottom side, which is actually quite interesting. Still, in terms of numbers, mode 0 is a bit worse than mode 1. But you see, even for mode 0, it actually works quite well. And then the hybrid model with the same codec being used for the re-encoding as the one that has been used initially is, as you can see here, quite similar in performance to the M3. There are a few outliers here, which with less outliers here, but still there are also in the hybrid, sorry, in the M3 model, there are a few outliers. And then you see more outliers and a slightly less good performance in case of this a different codec being used for the re-encoding. Okay, and then we have applied this also for gaming video quality analysis. So here the idea was, okay, so the advances in passive and interactive gaming services, cloud gaming, and they're of course more becoming more and more popular. And how can you actually handle, or how does the model perform when it is gaming specific content? I mean, the phase 2 in Peanuts was of course focused on any kind of content, so not dedicated to gaming. And the question would now be, okay, if you have this very specific type of content, how does that actually affect the overall performance? And we have been using 4 data sets that has been partly done in collaboration with the creators of those data sets. You see in the references. I will also upload the slides later on. It's this GVS, QU, GVD, and CGVDS, and NV and C data sets. We also have used a proprietary Twitch encoding data set, and then these 3 here, they are publicly available. Here, the maximum resolution being used was 1080p, so there was some remapping required because the original models that were in 4K. Okay, and the AVQ bits models were evaluated out of the box, so there was no dedicated retraining. And the comparison, the mode 3, mode 1, and the hybrid mode 0, they perform on par. And then for the mode 0, if you do a dedicated retraining, there's considerable potential for accuracy improvement. If for those who have been there in the Q14, so question Q14 ITUT study group 12 part that I briefly introduced in the IRG presentation, there I mentioned this PBQCG work item, and so this obviously is somewhat relevant in this context because it's also about parametric models, also passive models for cloud gaming. Yeah, and if you compare it with state-of-the-art models, then the best performing pixel models, again, of course, BMAF and NDNet Gaming is actually also quite good as no reference model, which came out of this database content. Yeah, and these 3 models here, mode 3, mode 1, and H0, they perform on par with BMAF and NDNet Gaming. And the AVQ bits M0, they outperforms traditional no reference models, Prescant and Leak for these cases. And this is again shown here. So again, mode 3 here on the top left, mode 1 here, mode 0 here, and then the 2 hybrid versions here. And you can see that overall the unfortunately, we didn't add the exact performance numbers in terms of RMSE, but you can find all the tables in the respective IEEE Access presentation. So also these different applications here are mentioned therein. Okay. Last one in terms of different applications, 360 video quality. So here the data set is this data set from this 2020 publication here. Which is a 360 video quality streaming data set. It's a full frame streaming, so it's not tile-based streaming or anything. 3 different tests, and the source content duration is 30 seconds, resolution 1080p up to 8K, and 2 different head-mounted displays being used, HD Vive and HD Vive Pro, for the respective tests being analyzed here. Yeah, and again, AVQ bits models were evaluated out of the box, no dedicated retraining. AVQ bits comparison, so again, mode 3 and the hybrid one, they perform on par. M1 and M0, they have a lower accuracy as expected. And with a dedicated retraining for this particular type of content, there is a potential not so strong in these first trials accuracy improvement. So these ones are certainly not so good when it comes to this 360 video quality. Comparison with state-of-the-art models, best performing pixel is VMAF with a center crop version. It's described in this paper here. Then VMAF, and then this WS SSIM. So a 360 adapted version of SSIM, and M3, the AVQBits M3 and H0, they outperform pretty much all of these for this particular application. Of course, the comparison could have been taken even wider, so we are aware that there are also more recent 360-degree video quality models, but it was only really to basically indicate the versatility of this approach, that it can also work with 360 video out of the box. It was not a paper on 360 video quality alone, obviously, right? So that's just one aspect. And you can see also really for mode 3, it actually works really well. Mode 1 still kind of works well, but then you see for mode 0, you can also see this, the predicted MOS. Obviously, you have very similar values because the database has very similar settings, right? So you have these kind of horizontal lines, and then obviously the real MOS is quite different from this. If you then again take the hybrid model, which uses only the information about what codec it was, what frame rate, bit rates, and what resolution, and then you basically you re-encode with such information the respective decoded bit stream. You again get very high performance, which is almost on par with the Mode 3 model here. Yeah, and then we have also created an integration module. You know, that's in this Peanuts phase 1. There has been this already a bit older. There's this P1203.3 standard. There's the architecture has an output which is called O3.5, which is basically an integrated audiovisual quality. It's not the final audiovisual, so the final output. That's O46. But this output here has been modified over this one here. The reason is that our models now, they are much more precise than these old phase 1 models, P1203.1 video quality models. They are relatively coarse, right? They're all mode 0 ones, and there's also, that's not completely true, there's also mode 3 one, but still that's only QP based. So finer quality degradations or variations, you don't see that. And so this integration model uses a per 1 second audiovisual input, so both for audio and video quality, which is based on the respective video and audio quality models. The audio quality model is basically untouched. The video quality model is now replaced by these different versions that I have shown you. And then you can see that, especially for the Mode 3 version, due to the fact that we have this random forest model included, it can follow smaller quality fluctuations actually more precisely. And then that actually generates some additional input, which is this kind of quality fluctuation, so to speak, which is erroneously educating this initial integration module to be a problem, right? And when we actually could train this and compared this with available test data from the Peanuts phase 2 context and own ones, then it was clear that this would be too fine granular, right? The way in which this old integration module was handling things. And so we replaced this. So we use basically all the core component of this one, which actually also has been strongly co-developed by us at the time. And so we have a per 1 second audiovisual quality score, which is capturing the temporal effects related to video quality fluctuations. But now this, it's a bit, what should I say, the biggest or the most sensitive component, so to speak, responding to these fluctuations has been removed. And this new integration module is now added as an appendix to P1204.3 as well. And so you can also predict quality for up to 5-minute-long sequences. And that may include things like stalling or initial loading or quality fluctuations, right? So it would be for an entire short streaming session. Okay, and this is evaluated on the UHD1 long data set, which has been published more recently by our group. It was created as part of the Peanuts phase 2 competition, but was not part of it. And then there are 5 tests conducted by 4 different labs. 1 test conducted by TU Ilmenau. So we also were able to use the Peanuts phase 2 competition data for some of them. So it's a collaboration among multiple labs from Peanuts phase 2, and the source content duration, as I said, is 1 to 5 minute long, and the context is mobile and TV. And here the distortions are video quality switches, initial loading, delay, and stalling events, as initially mentioned. Yeah, and the Mode 3 model, obviously, I mean, if you have a very good short-term quality model, then obviously also the long-term integrated version is performing well. Then the H0 version, the overall prediction accuracy is lower than with the M3. That's actually unlike the short-term video quality. That's also something we're currently looking into in more depth. This additional mapping of the per 1 second scores, that we're considering that as a way to increase the overall prediction performance when you are integrating the short-term video quality scores that are coming out of the H0 model. Yeah, and then for mode 1 and mode 0, obviously you get a lower prediction accuracy because the starting point is already worse. And the reasoning here is that that we use this, if you have a certain segment, we're using obviously the same per 1 second quality score, so there's no optimal handling of any kind of temporal effects, right? Because the overall setting for a given segment is identical, and the segment may be, of course, longer than 1 second. And if you really go in with a bitstream analysis, you may see more variation also during this shorter time frame. Yeah, and here you see the results. So 4.3 again for the long database looks quite good. The HOS still looks quite good. It's a bit worse than in the short-term video case, but you see the two are relatively similar. Even if you use another codec for re-encoding the decoded pixels, it's still quite good, right? So these look all quite good. And as you see for this kind of long-term integration part, the mode 1 and mode 0 are not so bad, right? So you have a bit more outliers, but overall the picture looks still quite nicely correlated here. And again, all the numericals, for timing reasons, we have not added all of this. It's in this Access paper, which is anyways open source. Thank you very much for your attention, and I'm very happy to answer your questions.
Thank you, Alex. Are there any questions?
I can ask a question.
I see Hadi.
Yes, thank you very much, and very interesting, and lots of evaluation analysis on different actually applications. So recently I was working with this bitstream based actually quality metrics, but what I was found that this bitstream parser is quite slow. So do you know that is there any optimization is ongoing on that or not? And can you please elaborate a bit more on the
yes, yeah, it's a super valid question, obviously. And so what we're currently doing is we are indeed trying to or not we're trying we're in the process of developing a skimmed down version of a bitstream parser, because we're not using all the features, right, that could be retrieved from such a parser, right? And also even the parser that we have currently made available open source with code at the time is principally able to put out even much more information than what the model is finally needing, right? So it's exactly what we're currently working on. We're also working on an extension to AV1, and therein also this kind of slimmed down bitstream parser would be used, right? So that you really just use you just extract the information that is needed to get the model calculation out. But in principle, the model itself is agnostic to the bitstream parser, as long as the bitstream parser actually provides you with the right output information.
Yes, actually, I was expecting that the maximum time that it should take is the decoding time, right? So we decode the bitstream, and we can get, but it was much slower than decoding time.
Yeah, it's not optimized. It was, I mean, the code that we actually published at the time, you know, it's not like it's university code. Let's say it has been actually submitted to the competition. It is not at all optimized for some real-time application, right? And I think it would be super interesting if people here are finding this approach relevant, right? Then this would be, of course, great to integrate this more tightly with other bitstream parsers, which are actually running faster, right? It's just a tool in our case, really.
Yes. Yes. Thank you very much.
Very welcome.
Thank you, Hadi, and I see Sahid raise his hand next.
Yes, can you hear me?
Yes,
I can hear you, Sahid.
Yeah, a very nice presentation, Alex. My question is about this HOF when you are encoding, re-encoding to create this quality equivalent bit stream with a different encoder. Do you also use some mapping like, for example, QP of this much for H.264 is QP of that much for HEVC, or you don't exploit this information? It's plain encoding. How do you make sure that they are equivalent? On what basis? Yeah.
No. I mean, we're then, of course, using the respective bitstream based model, which is individual, basically, for that re-encoded version, and that actually creates the deviation, obviously, right? That is why it works a bit worse, right? Because it obviously has a completely different approach to analyzing the data. Yeah. I think for the in-depth answer, maybe I contact you offline, right?
Sure.
It's more, we would need to look into the code in more depth, but it's not like really at a super detailed level that you would be doing, because maybe you don't actually know what codec has been used, right? That was the idea, and or you don't have it at hand, and so what can you do in case that happens, right? And then you know, this other encoder is being used, basically.
And an associated question is that is it like one attempt, or it's like multiple probe encodings you do to come to the right one, right equivalent bitstream?
Okay. No, for if you have the mode 0 bitstream information, we really take that as the input, right? And obviously you could argue now, if you have a super well tweaked encoder from company X, right, then it will not work so well, right? I mean, obviously we were using now an encoder which is really very similar, and that would be a very interesting field of study also, right? I mean, what's the, you know, what are the changes in terms of performance when you have some differently optimized encoders? What we have seen is that the mode 3 model is relatively robust against even some more kind of proprietary encoders, right? Definitely more robust than you know, some kind of hybrid model which presupposes this kind of re-encoding.
Thank you, Sahid. Lucas, you're up next.
Yeah, thank you so much, Alex, for the really detailed deep dive in that. I'm mostly asking about the evaluation process, because I know that there were some databases that were not named, and I'm just wondering, did you look into cross-codec performance? So if you had a database that would have different codecs at the same time, because I know that you have used different modes within the bitstream parser or within the module after that. So is it valid, like if you, for example, would have H.264 together with HEVC, if it uses these two models, would it still be as well correlated as expected?
You mean transcoding, or you mean both in the same test?
I mean, in the same test, if you just had the bit streams that are coming.
I mean, in the competition at the time, we also had databases which were not containing just one codec, right? So they were relatively varied, right? So for the mode 3 model, I would argue that this is quite well handled, right? So I think there shouldn't be any issue. So if I understand you correctly, just to be sure, you mean some sort of codec specific bias almost that is intrinsic in the test, because people may have been trained on a specific degradation that is particular for that codec, or what exactly are you referring to?
Yeah.
Okay. No, that should be avoided by the design of the test, I would argue.
Thank you, Lucas. Sahid, you still have your hand up. If you don't have a follow-up question, do you?
Yeah, I will lower it. Sorry for that.
No problem. Andreas, you're next.
Yeah. Thanks for your presentation. I had a quick question. I think in some slide you presented evaluation on 360 video. And that question, did you retrain anything or whatsoever? Because in our case, we tried for 360 video. We've also, but it is something I presented maybe 2 days ago. But we had to scale some factor like the bitrate or the resolution, and to have some factor to obtain the best performances that we could get from your model. I think from the P1204 mod 3 and also the P1203 mod 0. We apply some scaling. So can you clarify a little bit on that? Thanks.
Yes, there is also, sorry, I would need to look up this detail myself. Can I take it offline? I'm sorry about this. As I said, I may not be perfectly able to answer all questions because I'm not Rakesh. I need to look it up again. It's a very valid question you have. Yeah.
Thanks.
And it would be very interesting to exchange also if you have also used our code, with your experiences with it. So it would be great to connect offline, actually.
Yeah, sure. Yeah.
Thank you, Andreas. And I think you know Andreas very well. You have your corresponding emails. Is there any other question for Alex? Again, thank you so much for the very nice and very detailed, as always. Alex's presentations are remarkably detailed. But if there is nothing else, I think, shall we, for the first time, we are ahead of schedule? Oh no, of course, we have Jingwen and Hadi. Yes. So we're going to hear about one of my favorite topics, which is just JNDs, I guess, right? Or
yes.
Anyways, I leave it up to you. So are you going to be presenting Jingwen or Hadi or both?
Yes, I will present, but Hadi is here also. We can answer questions, take all questions together.
Very good. Take it away.
How to? Can you see my screen?
Yes, we can. Very well. And a laser pointer as well.
Okay, so hello everyone. My name is Jingwen. The title of my presentation is Enhancing Satisfied User Ratio Prediction for VMAF Proxy Through Video Quality Metrics. This is co-work with Hadi, Ramon, my PhD supervisor Patrick, and Christian. So first, why we are interested on it. We know that in per-tato encoding, each video content is encoded at multiple resolution in different bitrate. And then convex hull is formed based on the quality of encoded video. And bitrate resolution pairs are selected from the convex hull to construct a bitrate ladder, which can be used for adaptive video streaming. The research question here is which encodings to select from the convex hull to construct per-tato encoding bitrate ladder for video, which can be more optimized. So one effective or optimal ways to select representations from the bitrate ladder from the convex hull is to consider GND. So the GND here is video-wise, just a noticeable difference. And by using GNDs, it can help us to reduce the representation redundancy, quality redundancy, and it can help us to reduce the storage and the transmission cost. So we would like to use GND for bitrate ladder constructions. However, GNDs are different from one person to another person. So that is why we would like to introduce the concept of satisfied user ratio. So as UR curve is determined by GND of a group of viewers. Supposing that we have a source videos, we encoded it with the, for example, QP from QP1 to 51, and we present, we ask a group of observers for the GND subjective test to determine the GND of these videos of each observers. And from the subjective test, we can get distributions of the GND of each observers. Supposing that these distributions follow Gaussian, we can obtain the probability density function, PDF, of the distributions. And we can obtain the CDF. Then the cumulative distribution function could be obtained from the integration of the PDF. And the SUR is defined as the complementary of the CDF, 1 minus the CDF. So how we can understand the satisfied user ratio when we can see in this green curve, when QP is very small, SUR equals to 1, which means everyone in the population cannot detect the distortion. They are satisfied. And when QP is very large, the SUR equals to 0, which means everyone in the population perceives the distortion and they are not satisfied. In literature, the most commonly used GND threshold is 75%. So here in this case, when QP equals to 28, SUR equals to 75, which means for the video QP equals to 28, there are only 25% of the population can detect the distortion, and the 75% of the population they don't see any difference. Okay, so the previous example, the proxy of the SUR is QP, but what about the VMAF value of the 75% SUR? We are interested in VMAF because it is widely used to evaluate the quality of encodings, and it is not constrained to any certain codecs. So we analyze a public available GND dataset, video set, which was mentioned by Yanni the first day of the meeting. So it includes 225-second SRCs, and each videos are encoded with H264 QP from 1 to 51, and there are 4 resolutions for each content. So we compute the VMAF scores of the encoded videos who has SUR values equals to 75, and we plot the delta VMAF across the entire dataset for 1080p. The delta VMAF SUR 75 equals to 100 minus the VMAF score of the video who has the SUR score equals to 75%. So we can see that this delta VMAF is really content dependent. So for example, here we can see there are some videos when the VMAF score, when the delta VMAF almost equals to 25, which means the VMAF of these videos are around 75. There are like 25% of people, only 25% of the population can detect the distortion. And there are some other videos which the delta VMAF is almost 0, which means their VMAF scores are 99.9, and they are already 25% of the population detect the distortion. So because the delta VMAF is very content dependent, can we predict it for different content? There are some of the previous work try to predict the delta VMAF. However, the prediction error are still quite big. So here is how the previous set of art for predicting VMAF works. So we can see that it extracts features from the original videos, SRC. It's the features like SITI, VCA, frame rate, colorfulness, etc. And then they put these features to the regression model to predict the delta VMAF for certain SUR threshold. And in this work, we don't extract the features from the original videos. We just try to compress the original videos to a certain QP, to an optimal QP, and then we try to compute the VQM of this fixed QP, these videos, VMAF, SSIM, PSNR, etc. And then we put this video quality metrics scores as features to our regression model to try to predict the delta VMAF. And how we select which QP to encode, how we select the optimal QP, we just try every QP, every possible QPs, and pick the one that gives the smallest error. So here is the experimental result. The first two model is a fixed VMAF prediction paradigms, which the first one takes delta VMAF equals 2, next one takes 6. We can see the error is quite big. And this one is previous work of Hadi, which they try to extract the features to predict the delta VMAF. And the rest is the result of our work, which takes VQM scores as features which takes the VQMs of the optimal QPs as features to predict the delta VMAF. We tried we reported result of 2 different regressor and a different combination of the input features. And we can see that using XGBoost with VMAF and SSM as input with optimal QP value 28, we obtain the smallest MAE, the best result. And we also analyze the feature importance by concatenate all the features. It can be observed that the VMAF and the SSM are the most important features compared to other video complexity features. So the conclusions, the first very important conclusion is that delta VMAF of the 75% ICR is content dependent. And the second is using VQM of a fixed QP, compressed videos as input features outperforms using content features such as video complexity features, etc. For the delta VMAF prediction. And the third is by using VMAF and the SSM of QP28 can help us to achieve the best prediction error. Thank you. Any questions?
Thank you very much, Jingwen. I love it. And I already have 2 quick questions for you. I mean, you know, I love every work around JND, right? So it's like one of my favorite topics. Did you try to include the bitrate as a feature apart from VQM?
No, it's just the quality scores, VQM score.
I'm guessing bitrate could maybe not as important as VMAF and SIM, but it's a very cheap metric, right? It comes for free.
Yes.
The bitrate of a certain QP, right?
Yes, we could try that. Yes.
So my suggestion is to try that. And the second, do you have the average VMAF you obtained at QP28? Because my guess is going to be around 80.
The average VMAF score of the QP28.
Anyway, if you don't have it now, you can give it to me offline. But I would say, based on my experience, and that's one of the reasons why in our proposed grand challenge we choose the QP, the VMAF 80 value seems to have the maximum amount of information for the content. But I would love to get that statistic from you.
Yes.
I know it's in the database, but I will stop here because I see Francois raising his hand, and
okay, I can check it and send it to you by email if you want. The average of QP28.
Thank you, Francois.
Thank you. Very good presentation, Jinwen. A question: you use this ratio of 75% and 25%, and if I understand correctly, you said that 25% of the population will notice the degradation.
Yes.
That's correct.
Exactly. Yes.
And do you think that that's still high? Like that's a large portion of the population. So was there a reason why you selected that ratio?
Yes. I would say this is the question every time. Every time I make a presentation, there will be someone asking these questions, and I cannot really answer it very good sense. But why we choose 75 at the beginning is because all the literature use 75. But then with Hadi, we decided to take this question seriously. So we did some analysis based on the trade-off between the bitrate and the threshold of the satisfied user ratio. Like, for example, to satisfy 80% of people, we need to sacrifice much more bitrate. So the results shows that the 75 is quite a good compromise. And this paper hasn't been published, but yeah, this is a very good question. I think you can also adapt it based on your use case, like based on your budget, how much people you want to satisfy, right?
So have you done this? I guess if bitrate efficiency to satisfied user, where you get the most I guess return. I don't want to use the word return on investment, but it'd be good to see that, or maybe that's the curve here, like bitrate.
It's not. This work is not here. It's another work we submit to. It hasn't been published, but we have this analysis based on the bitrate trade-off between bitrate and SUR threshold. Maybe in next VQEG meeting, maybe we can present it.
I'll make sure that I ask the same question then. Okay, good work.
Thank you.
And thank you again. Before we move to Lucas, who is next, and Dietmar after, I have to admit or take part of the blame or credit for this P75. So if everybody asks you, you can say, Jingwen, ask Yanni for this.
Okay.
But truly, when we did the original JND design, we went through a number of definitions of JND, and it really, at the end of the day, falls down to the just noticeable difference. Just noticeable difference is always a statistical quantity. And as Jingwen said, most studies that I have seen, not only for visual quality, but for other stimuli, right? When it comes to taste, smell, or other, sensors, people have traditionally been using historically the P75. But other than that, I would love to hear if there are any more explanations from experts in this field. Lucas, go ahead.
Thank you. Thank you.
Thank you very much, Jingwen. As always, really interesting stuff. I'm wondering, I have two questions. One of them is, do you know if the content dependency actually does depend on the satisfied user ratio? Like, for example, if we had a 95%, would it be less content dependent when it comes to VMAF predictions or not?
Oh, good question. We didn't, for now, we haven't checked. I should check it. I think for how to say, for lower SUR, for sure it's very content dependent. Actually, this happens previous, not this one, sorry. For example, this happens like very low VMAF score, very high delta VMAF score. This happens is from certain QP, the VMAF decrease very sharply. I don't know how to say it. So for sure, for lower SUR is content dependent, but for higher SUR, I haven't checked. I should check.
If I may offer, again, this is, we've never published it, but again, when we did a similar analysis, we actually found the opposite, Jingwen. Because of the, let's call it Gaussian approximation of that curve, if you go back to your PDF. Go back to your PDF. Can you go back to the PDF? Yeah, this one. You do understand that the P95 corresponds to roughly the outlier of the distribution. So the outlier of a Gaussian distribution that you sample n times has a much higher variability left or right compared to the median, which is the P50. So again, there will be differences, there will be content dependency, but our preliminary study showed that the P50 would have the least amount of content variability compared to 75, 80. Yeah, but again, I don't want to be talking about things that I went to whatever
I should check,
8 years ago, but this was a preliminary signal. But I see Dietmar raising his hand. Dietmar?
Yes, thank you very much. Very nice talk. I like the topic, of course, because we're also working in the area of video JND together with Mohsen Ginadele. And my question is, maybe I didn't understand the method quite right for the prediction. What I understood, but it seems hard to believe, is that in order to predict the delta VMAF, you only need two numbers, namely the SSIM and the VMAF at one particular quality parameter 28, you said, or 29, or whatever it was. So just two numbers, and from those two numbers, you can predict the delta VMAF. Is this correct? Or is there something more?
Okay, so I think your understanding is correct. We just, for example, how we use this model, we have the original video, we encode it with QP28, 28, and then use the VMAF and SSM scores of this
Yes.
QP28, put it in the regressor, and then we can have the prediction of the
Yeah.
delta VMAF
So-
good results. Why this happens is because we are using VMAF to predict the VMAF. Actually, we use why we picked the QP28, so we kind of have this information how VMAF perform based on this video content, and the VMAF score include the information of how this video perform based compress. I don't know how to say how this video perform based on the compression, and then try to predict this delta VMAF. We were very also surprised that this outperforms based on the features extracted by the original videos. I think this is because we have this compression, and we can get this information of the compression based on the.
Yeah, you could also, compute the VMAF and SSIM for more QP parameters, maybe for all of them, and then you would have maybe a better regression, a better result. Or did you try that?
Yes, we tried that actually. We first tried one compressed video, and then we tried two, and we see that the performance is not that better improved, but then we need to compress twice. So here we decide to put just the one optimal QP.
So that's very nice. So you could put in your presentation or in your paper just a simple formula. It's a function of the VMAF and SSIM at QP28, and you can just write it down in one line.
Okay.
And if it's a linear regression, it's just a linear combination plus some offsets.
Okay.
That should be included. And my other question now is, you started out with the motivation, and the motivation was this bitrate ladder.
Yes.
The bitrate ladder, you need more JND points now, the second, third, and fourth.
Yes. Yes.
And for this, you also need to have some prediction method. Are you proposing to use the same, but only applied not to the original source, but to the one that is at the first JND? Or?
Okay, so this work we just focused on first JND, which and then for other JND to construct the entire bitrate ladder is also very important, but not yet investigated.
I understand. Thank you very much.
Thank you, Dietmar. I know that your group is actually one of the most active ones, just like Jingwen and Patrick's group on JND. So looking forward to further work on this topic. Unless there are any questions, we are only 10 minutes over time, I guess. Hearing none, back to you, Sel and Margaret.
Well, very nice that we're only 10 minutes after.
Yeah, I agree. Yeah. So should we try to take this this picture? I don't know how to do it in Zoom, but I guess everyone needs to at least put on their cameras. I guess that's the starting point. Maybe we stop the recording now. I mean, I guess there is some kind of still picture feature in this